Hey guys, BuildZoid here, and this does not work. I mean, it runs, but it does not work. So the idea behind this abomination here is if you've ever touched the back of a CPU socket on a running system when the CPU is under heavy load, you've probably noticed it's pretty hot. Um, and so that gave me the idea, because I've done that. What if we made the back of the CPU socket not hot? By, say, applying a 280mm AIO, though I do only have one of the fans running on it, so, yeah, anyway, that's fine, because there's really not much heat being generated back there. Yeah, what if we, like, cooled down the back of the board? Would that make the CPU run cooler? Because, quite frankly, there's better ways to cool your VRM than, like, water cooling the back of your board. Like, putting a fan on it, or, if you must, water cooling the VRM. Um, but yeah, so I got this lovely idea of like, well, we just put an AIO on the back of the board at the same time as an AIO on the front of the board, and then we run Prime 95 with a 10900K on a Gigabyte Z490i Ultra, and this is just the only Z490 ITX board I had on hand, so that's why I'm using it. Thank you, Gigabyte, for the board. Yeah, we run Prime 95 at 1.26 volts die sense currently, pulling about 250 amps out of the VRM. Yeah, we see if we can get the temperatures of the CPU to improve by applying the second AIO. The answer to that question is no. It does not improve the CPU temperatures by any appreciable amount. The VRM is way cooler though, but like in both configurations, like you can see I have a VRM cooling fan on the in front of the board down here. I had that even when I was testing it with the single AIO instead of the CPU cooling sandwich. Um, and without the sandwich, the VRM would sit at like 72 degrees. With the sandwich, it sits at like between 63 and 65 degrees. Um, so, yeah, the VRM's cooler, but that's not what I was aiming for at all. I was trying to cool the CPU down. Um, but I guess I can't be too surprised. Like, I did pack the CPU, the cavity, the CPU socket cavity with thermal pads, because obviously I realized, like, think about it, right? Intel CPU sockets, they're pins that, like, make contact with the CPU with, like, needle points, right? Like the head of a pin, not very large, and the pin itself not very thick, right? Very fine, which is why it's so easy, like very thin, and that's why it's so easy to bend them. Um, and so the thing about like trying to do heat transfer through thin pieces of material is that thin pieces of material do not have a lot of thermal capacity, like don't have a lot of thermal conductivity. So pins aren't really great thermal conductors. The rest of the socket is made out of plastic, and what isn't made out of plastic is just filled with air. So basically, CPU sockets are, especially like LGA ones, are probably about as not thermally conductive as it gets. Okay? I don't really think there's a way to attach a chip to a board with worse thermal performance than an LGA like with like worse thermal transfer to the board than an LGA socket. Which is why I packed the CPU socket cavity, that's the empty space in the middle of an Intel socket, with a bunch of thermal pad. Um, but the thing is, there's capacitors in there, and sockets are actually surprisingly deep. Like I was really worried when I pulled out like my best thermal pad is the like highest thermal conductivity thermal pad I have is 2 millimeters thick, and I was really worried it would be too tall. Turns out it wasn't tall enough. I actually had to put like it wasn't two full height layers. It's not like the socket isn't 4 millimeters deep or something, but it isn't. It's deeper than 2 millimeters, and that's to the tops of the capacitors. The PCB of the motherboard itself is even deeper down than that. The PCB of the motherboard is probably down at 4 millimeters relative to where the CPU ends up resting when you clamp the CPU sandwich down on it. So basically, CPU sockets are very tall, not very thermally conductive, And thermal pad, in the grand scheme of things, also isn't really that thermally conductive, especially when you compare it to, I don't know, like indium solder and a copper IHS, right? Um, so packing the socket full of thermal pad probably didn't like it probably made the socket way more thermally conductive, but compared to the actual heat spreader, it basically didn't make a difference, I don't think. Um, and then, of course, because so now that we've got the CPU from the back of the CPU substrate into the CPU socket, some of it, right? Like some heat would still transfer. Like as long as the thermal pad is at a lower temperature than the back of the CPU, heat from the back of the CPU will enter the thermal pad. And as long as that thermal pad is at a higher temperature than the capacitors in the socket, from there it'll transfer to those capacitors. And as long as those are at a higher temperature than the PCB of the motherboard, the heat will transfer into the PCB of the motherboard. And then finally, on the back of the motherboard, right now we've got the heat in the motherboard. Well, now we hit another layer of thermal pad, but there's also more capacitors on the back of the motherboard. So we have to go through those, and then there's more thermal pad again. So there's sort of like the back of the board is a sort of mix of thermal pad and capacitors at the same time. And then finally we get to the AIO. And the AIO is definitely the coolest part of that equation, because the water in the 280 here currently, the hot side of it is at around 27 degrees. The cold side of it is at around 26 degrees. So there is actually heat getting into it. It's just not from the it's not from the CPU. And the reason I say it's not from the CPU, at least the vast majority of the heat that's getting into that 280 millimeter radiator is not from the CPU, is because the VRM is currently sitting at 63 degrees Celsius. Whereas when I did this test without the AIO, it was sitting at 72 degrees Celsius. And I believe I've just repeated myself. I might have said the exact same thing at the start of the video, but I've been awake for kind of too long. And so, yeah, I do apologize for that, but I have no idea what I said in like the previous take, so, or at the start of the video at this point, so that's great. Um, um, anyway, yeah, so the VRM's running way cooler. The CPU really isn't, and I'm, pretty disappointed about that. But the other thing, like, that we're not just going to stare at this abomination here. We're also gonna take a look at some math, because like just theoretically, like what would make this setup worth it, in my opinion, is like, well, let's say a 10 degrees Celsius thermal improvement, okay? Right? That, like, if putting water cooling on the back of your motherboard made the CPU 10 degrees cooler, I think it would be worth it. So, let's do that. So, currently, so in the unsandwiched test, the CPU would average around 98 degrees, and the water temperature, and I just pressed the wrong symbol, the water temperature was 40 degrees Celsius. It turns out 240 millimeter AIOs have a pretty hard time dissipating over 300 watts of heat. In terms of heat output, we're averaging a little over 300 watts. I'm going to make it simple. We're going to say 300 watts. So we've got like a thermal resistance on the front of the cooler, right? On the the thermal resistance of the silicon, the solder, and the IHS, and the thermal paste on top of the IHS, and the cold plate of the water block combined is 0.19 degrees Celsius per watt, which is pretty low. Actually, is really low, I think. I don't know. I don't have a good reference against that, but I'm pretty sure that's very low. Anyway, so 0.193 degrees Celsius per watt. So if we wanted the CPU to run 10 degrees cooler, roughly, like the thing is, we can't, like basically our goal is to like pull heat from the CPU, right? The CPU produces 300 watts of heat. Our goal is to pull more heat out of the back, like some amount of heat out the back of the CPU, so that doesn't have to go out the front. So in order to actually achieve a useful temperature improvement, we would have to go like 50 watts through the back of the socket. Because if we did that, and then we multiply it by our 0.193333, we get a temperature difference of 48 degrees between the water and the CPU. So if the water was still at 40 degrees Celsius, which it wouldn't be, the water would actually end up being cooler because there'd be less heat entering it, so the radiator would have less heat to dissipate, so the water temperature would be lower. Which actually, this just goes to show you how freaking ineffective this is, because the freaking CPU temperature has like not improved by a measurable amount. Which means if the rear AIO was doing anything, like this should have, like, the thing is, this should snowball if it was actually working somewhat. Like, it should somewhat snowball, because if you pulled a significant amount of heat out the back of the socket, then the water temperature at the like the front rad would have to do less work because there'd be less heat for it to dissipate, and the water in it would be running cooler. And cooler water means cooler CPU, assuming the thermal resistance hasn't changed and there's less heat to dissipate. So yeah, and obviously this is like a grossly simplified way of thinking about it, not this isn't super accurate, but like, yeah, basically if I wanted a 10-degree improvement, we'd have to suck out like 50 watts of heat through the back of the socket, which is like, yes, not happening. But the thing is, like, I'm getting like no degrees temperature improvement. So we're probably not even pulling 10 watts out. Not even 10. And so that's kind of annoying, but the fact that the VRM is like 7 degrees cooler makes me suspect that all of the heat that the AIO is pulling out, because the AIO is above room temperature, like the 280 millimeter is above, like the back of the socket AIO, it's above room temperature, right? There's a temperature delta across it, so there's heat entering it and leaving it. It's just not heat from the CPU. So yeah, and unfortunately, it's just like in order for this to work, you would have to pull a lot of heat out the back. And the thing is just like the thermal resistance of that, like lots of thermal pad capacitors. Well, actually, it's not even that. Like, you have this, so the heat gets generated in the CPU, then you have the substrate. So you have the substrate, the thermal pad in the socket, then the PCB, then the thermal pad on the back, and it's like, yeah, I can see why we can't get anywhere near, like, how it's like, I can totally understand why I can't pull anywhere near 50 watts of heat through that, stack up of materials, because most of those aren't particularly well known. Like, most of those are, like, yeah, they're more thermally conductive than air, but that's not much of a, not much of an achievement. And also, there's like probably the equivalent of like 6 millimeters worth. Like, I think there's like a 6 millimeter gap between the back of the CPU and where the AIO actually is, which is like, if you had a 6 millimeter like copper spacer, it would probably be pretty bad for your CPU temperatures. But this isn't 6 millimeters of copper. This is like 6 millimeters almost entirely made of thermal pad. So it's like, yeah, I mean, I don't know what I expected. Actually, I didn't really expect anything. I was just like, well, the back of the board gets hot. Maybe we could lower temps if we made the back of the board cold. Well, the back of the board is now cold. It's not actually cold. Thermal pad really isn't that great, but especially when it's 2 millimeters thick. But I can't do anything about that. There's capacitors on the back of the socket. We don't want to crush those. We really don't want to crush those. Anyway, or like, I guess you could remove all the capacitors on the back of the socket, but that's just like, please don't do that. Please don't do that to your motherboard. Well, actually, to be fair, there's been motherboards in the past that were produced with no capacitors on the back of the socket. I'm not a fan of that, but they do exist. Anyway, yeah, so like the back of the board is definitely now colder, but the CPU isn't. And I think most of what I've done is just cooled. Like, actually, no, it's not even. I don't think it's like I can clearly see that most of what I've managed to do is just cool down the VRM, which is like, well, that's great and all, but that's really not help. Like, that's not useful. So yeah. So on Intel CPUs, this definitely doesn't work. On AMD CPUs, I don't think it'll work for like I don't think it would be worth trying to do this on an AMD CPU because well, AMD CPUs tend to have really high thermal resistance and produce tons of heat. Actually, they have really high thermal resistance, don't produce a lot of heat. But the thing is, like, if they have a really high thermal resistance to start with, like, I think in AMD CPU sockets, though, have lower thermal resistance than Intel sockets. Because Intel sockets, right, you've got those really, like, really skinny pins. Whereas PGA sockets, you've got those big fat pins on the CPUs. And those then get crushed into, like, there's, like, 2 contacts per CPU pin that the CPU pin gets sort of, like, squeezed into. And then, of course, there's more plastic than air in an AMD socket. Like, Intel sockets are pretty empty. Like, yeah, you've got the plastic, but there's a lot of air in them. Whereas AMD sockets, I think, have a higher, like, if you compared the ratios of, like, metal, air, plastic between AMD sockets and Intel sockets, I think AMD sockets have a higher metal and plastic content relative to the air content, so they should be slightly more thermally conductive, maybe even significantly more thermally conductive. Um, and so maybe that would make for a bit better, thermal transfer from the CPU to the back of the socket. At the same time, Ryzen chips don't produce anywhere near this much heat. So I'm not sure that it would necessarily, well, the thing I'm wondering about is like if you're running a 3950X, because I do have a 5950X, but 3950X is similar enough, and it's the CPU I have more experience with. That'll easily hit like 92 degrees Celsius if you're running it at only like 240 watts or something. And I think the water temperature is going to be kind of similar, so we're going to just take off, say, I don't know, 37 degrees. That's actually a lower temperature delta. Okay, yeah, no, that's not worth it at all. Because if you divide that by 240... Yeah, well, okay, no, that does give you a slightly higher thermal resistance, doesn't it? So with that, maybe if you went to 220... You could shave off... So if you pulled 20 watts through the back of the socket, you could shave off 5 degrees. That's basically the same as the theoretical 25 watts through an Intel socket. Then again, okay, you know what? I might test the AMD one too, just because it's not that difficult to... Like, this is not that difficult to set up. It's annoying to set up, but it's not actually that difficult to do. And... Like, yeah, it's super sketchy, but actually on AMD CPUs, it's much less sketchy because I had to remove, like, the socket bracket stuff for this. Where did I put the socket bracket stuff? I think it's somewhere in the mess of cables over there, so I'm not gonna... Anyway, like, the hold down mechanism is currently missing from this, so when I take this apart, the CPU's just the CPU's gonna just get stuck to the AIO that it's attached to, which I just don't like very much, right? Admittedly, the CPU doesn't have any pins on it, but the problem with, like, when the CPU comes out of the socket with the cooler that it's attached to, there's always that chance that it'll, like, fall off or something, or that if you do it at the wrong angle, you're gonna, like, break the pin, like, bend the pins, which, yeah, I don't really like unbending pins. But yeah, whereas on an AMD system, that's not really a major concern because the CPU doesn't just, like, well, the CPU shouldn't come out of the socket that easily. So yeah, I think I'm gonna do this with an AMD system as well. But at this point, now I actually have expectations, and those expectations are very, 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 very low. Yeah, they are really, really low. I guess I could have done this on a motherboard that has like a super ridiculously efficient. I don't think that would have helped though. Because there's also the power loss in the power plane itself, and we're probably we're probably cooling a bunch of that. Like a whole bunch of the heat that is generated in the power plane is just ending up in the AIO. Which is also why the VRM is why the VRM in this setup is running so much cooler. And so, yeah, that's also a problem with Ryzen systems. In fact, that's not necessarily, yeah, like that's still a problem with Ryzen systems. So that's just not gonna really. Maybe the Ryzen socket is lower, like less tall, but I doubt it. I really doubt it's any less tall. So, yeah. CPU sandwich cooling doesn't really work that well, but I think I'll still try it on a Ryzen. I definitely want to try this on a GPU because on GPUs, like, those are BGA, and solder balls are tiny, right? So, like, the chip is actually, and actually what's cool about most GPUs will actually have a BGA that goes all the way behind the core. So you just have like, because here in a CPU, if I hadn't put thermal pad in the CPU socket, if you think about how the heat would have traveled, it would have had to go, like, it would get generated in the die, then it would have to go sideways through the substrate, then into the pins, and then through the pins into the PCB. It's like, yeah, it's not gonna work. Like right off the bat with that, it's like, yeah, that's probably really, really high thermal resistance. Whereas with a GPU, you just have a BGA. Like there's solder balls literally going from one corner all the way to the other corner of the chip. You know, there's barely any there's very little empty space on the back of a GPU core in terms like air. I mean, it's still mostly air, not mostly tin, but there's a lot more, like there's a lot less, you know, it's far closer to the PCB, and there's a lot more metal relative to other materials, including air. So yeah, I think on a GPU this will probably be way more effective. On a motherboard, so on Intel, this definitely doesn't work. AMD, we're gonna have to, like, AMD, we'll find out. I think it doesn't work. GPU should work. Probably not that impressive. Probably not really worth doing. But it should still work. Whereas here, it's just like, yay, I cooled the VRM. Which is not at all what I was aiming for. Anyway, sorry for wasting your time. And I guess thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, and other, like, you know, the usual YouTuber. Is that it? Anyway, Teespring, there's merch. You can buy it to support the channel so that I can do more stupid stuff like this. Yeah. And it would be much appreciated if you check out the Teespring or the Patreon, because they do help out immensely with running the channel. And yeah, that's it for the video. Thanks for watching, and goodbye.